So today we discuss interference of light waves. So interference of light waves. So here we use two sodium lamp. Okay, two lamp, suppose S1 and S2 pinhole. Okay, out of wave from S1 and S2 pinhole. These are two ordinary sodium lamp. Okay, and illuminating these two pinhole. Okay, so these two wave, one wave, and there is another wave, and these will not observing any interference pattern. Why not observing any interference pattern? Why? Because these two sources, actually these two sodium lamp sources, are in out of phase. They are not in same phase because they are out of phase. Means they are incoherent source. Coherent source. Okay. So previous class we discussed how to addition of two wave and what is coherent source and incoherent source. Okay, and some basic idea when it create a bright spot or dark spot here. So here that's actually interference, means addition of two waves. So here these two waves, when you see the interference, these two sodium sources are need, very importantly, they are in same phase. So need to these two sources are coherent sources. Okay, so actually when we turn on these two lamps, so there is some the time difference here, that's why they are out of phase. When there are some millisecond difference, very precisely can measure, and here is a millisecond or nanosecond error, so they are obviously out of phase. So you do not observing any interference pattern. So here the Young modified the concept. So now Thomas Young experiment modified these two concepts slightly, and they said and if a source, a single sodium lamp, okay, and here is that pinhole single lamp, and here is another cardboard here, and here the two pinhole here, and here the pinhole is S, and that is the S1 and S2, the two pinhole here, and you see that there is a wave and passing from these pinhole, and you see that these two are a secondary source. This S1 S2 pinhole are create a secondary source, and you see that the sodium one light produces two pinhole here, and these two pinhole also are in same phase. The wave here out from these two pinhole are in same phase. Same phase. Wave are in same phase. So that's why these are coherent source. Okay, and these coherent source produce interference, and we place a screen here, and we get some bright and dark spot. Suppose some bright and dark spot. Need to place a thing. Okay. This. And these are the bright spot, and these are the suppose these are the called dark spot. Okay. Bright, and say that is, and these are called a dark spot. Okay, so that's the interference. That's the interference. Pattern. Okay, clear the concept. What is the interference? How Young modifies? And here the one lamp. So actually that one lamp and passes through these two pinhole, and these are the same wave, and these wave are in same phase. So that's why the coherent source, and these two S1 S2 are in coherent source. So that's why they produce the interference. So here some calculation here, some calculation, basic calculation obviously. Some S1 and S2, S1 and S2, okay, and S1 S2, and these two pinhole produce a spherical wave. Spherical wave, yeah, spherical wave, S1 S2, okay, and here is the screen, and suppose we choose a point P here, and S1P, and here is S2P. Okay, that's the S1P part, that's the S2P part. Okay, and the gap between S1 and S2, suppose we say that is called D, small d. And from source, obviously the secondary source to screen, the distance is called capital D. Okay, and there's a midpoint here, there's the origin O, and OP here, O to P, this length P X O to P. Okay, and these actually the point here, there's a midpoint. Okay, the S1 S2 line and the midpoint here. So okay, this length, that is D by 2, and this length also that D by 2. Okay, so here there's a diagram here from Young experiment. So the path difference, so the path difference is, you know that what is the path difference, that is a S2P minus S1P, that is equal to n lambda, and where n equal to 0, 1, 2, so on. Okay, so here now from calculation, so S2P square minus S1P square, let's say, so calculate. So S2P, and see that the triangle, this triangle, from A and this triangle, a right angle triangle, there's a 90-degree here. So there's a S2P, that is equal to base, that is a right angle triangle from Pythagoras theorem, with help of this Pythagoras theorem. With a base square plus perpendicular square, we get a hypotenuse. This part is 2P. So that is a base square, that is D square plus this length from P to this point, that is a P to OX, that x to D by 2. So x plus D by 2 whole square. Okay, and now what is the S1P? So S1P, this path, and we similarly consider the A, S1 and this point, this right angle triangle here. So we apply the Pythagoras theorem. So S1 to some length here, that is a base, that is a perpendicular. So base square plus perpendicular, we get a hypotenuse square. So hypotenuse S1P, that is a base, is D square plus x minus D by 2 whole square. Okay, so now that is applied D square. Now here we get a plus b whole square. So that is x square plus twice x d by 2 plus d square by 4 minus d square here. So minus x square, because there is minus a minus b whole square, but here is minus, so that is minus plus minus x square plus minus minus plus twice x d by 2, and that's the minus, because the plus minus minus d square by 4. Okay, now we cancel these d square by 4, d square, d square. Okay, we get a final expression and obviously, oh sorry, x square also. So we get a 2 to cancel, twice xd. So here s2p square minus s1p square we get 2xd. So here s2p a square minus b square formula apply here, plus s1p, s2p minus s1p, that is equal to twice xd. So jump to next page. So s2p minus s1p, that's the path difference. Okay, there's a path difference here, that is equal to twice xd by s2p plus s1p. Okay, and this length s2p and s1p, s1p and here the s2p, these two length here. So apply some condition here. Some condition is say that is a small d. Okay, the condition is the small d is a much lesser than capital D. Okay, so if small d is much lesser than capital D, so now S2P and S1P are almost look like a similar. So S1P almost similar to S2P and also similar to the D length. So here the D plus D you get 2D. So that is equal to twice xd, small d obviously, that is a twice capital D, and this is the n lambda path difference. Okay, so 2 to be the cancel, and we get a very important term here, the x equal to n lambda capital D by small d. We get very important expression here, x equal to n lambda capital D by small d, where n is equal to some small number here, that is n equal to some 0 plus minus 1 plus minus 2 and so on. Okay, so here that create a constructive interference. Here we create constructive interference. Okay, we get a bright spot here. Okay, now where we get a dark spot for destructive interference, so that is x equal to some n. Now the n we change here, so n plus half lambda capital D by small d. So n obviously same here, 0 plus minus 1 plus minus 2. So here is a fraction term, so that fraction term create a destructive interference, so that create interference. Okay, clear these two expression, that's the very important here. Okay, create a constructive interference and destructive interference. Okay, so we get a bright and dark band or spot here and appear on the screen. Such band are called fringes. So what is fringes? Very short question, you get 1 marks here. So fringes is that after solving the input here, these two expression x for constructive and for destructive CD. Okay, so the dark and bright spot on screen. Okay, so such band, such a spot or band is called fringes. This name, scientific name is fringes. So actually these lines are called, patterns are called fringes. Okay, suppose is a bright spot, so bright fringes, here create a dark spot or dark fringes. Okay, clear what is fringes and what is interference and what is a young experiment, young. Okay, the double slit experiment means a two pinhole here and two. Okay, so now we discuss another important concept is a diffraction. Okay, that's very important concept. Discuss diffraction. And before that we put a image. Okay, so Okay, and this image is an interference pattern. Okay, and here we get some bright spot here, and in between these two bright spot we get a dark spot. So these are called fringes. These are dark fringe, these are bright fringe here. Okay, these are called interference, not diffraction. These are interference. Interference pattern. Actually, interference pattern look like this. Okay, clear. So here we discuss what is diffraction. Diffraction is that when a single source, okay, here the single source also produces some pattern here, some fringes here. So when a two blade, okay, with two very sharp edges here, very close, and light passing from two sharp edges also create some pattern here. Okay, diffracted pattern is called diffraction. It look like this. Some okay, okay. This light source here passing from this gap, this pinhole, this pinhole, and suppose this pinhole length, suppose very small, that is a, and here I place a screen here. Okay, place a screen here. Okay, we get some bright and dark spot obviously. Okay, we get some bright and dark spot. So here middle we get very high spot. Okay, and now get another very high. Now get another. Now you see the width is narrower. Here it is high, but it's a little bit narrow. Here is very narrow. Here is very narrow. But actually intensity very high here. So here means this width is W. The width of fringes. This width of fringes is W, and here the intensity is very high. Here the intensity is very high, maximum intensity. But here low, there is a low, and so on. There is a low, low. Okay, so here we get maximum intensity. Intensity is maximum. That's the screen. That's the intensity. Is maximum intensity we get here. Okay, and now there's a gap from source to screen, that is a capital D. So we get some expression W. So W equal to width of fringes, that is equal to twice lambda wavelength of capital D by A. Okay, so here you see that in each point, okay, of a wave going to a gap, or a very small, a narrow gap, or a slit gap, or pinhole, as a source of secondary wavelength. These are source of secondary wavelength. Okay, passing from this light wave passing from this gap, we get a secondary wavelength. Okay, and this spread out the whole here. These are the spread out whole this region, and now we get some pattern here and some dark and bright spot here. Okay, so W is the width of the central fringe. Actually, the width is very large, so that's why these are the width of central fringe. The width of central fringe, and that is obviously the lambda is the wavelength. The D gap between the source and screen, or distance between screen. Okay, and A, this A, okay, A is a slit gap or slit width. Let's say it is a gap. These are the slit. Okay, here the single slit diffraction, and here double slit interference here. The double slit, young double slit experiment. Okay, the slit is actually the gap. There's a young double slit, and diffraction we get a from single slit. Okay, so if we double slit gap here, so actually double slit is look like this. Suppose double slit interference. Take some example here. Okay, suppose two gap here. Okay, and these two do the S here. Okay, and this small is a here with that is a, and there is a source. Obviously there is a single source. So okay, so that's why they are in same phase. So they are in coherent source. So coherent source also produce interference. Otherwise, if I use the two separate sodium lamp, they are in obviously out of phase. But here in same phase, we get some interference pattern here. So we get some bright and dark spot here. Pattern is looking. And now we get the expression width of the fringes, the W here, the W width of the fringes, that is obviously this gap with that D, so that is lambda capital D by S. That's very important for interference. Okay, if I combine the interference and diffraction, obviously here that a single slit also produces a diffraction here. So that is an important concept. If I combine these two, what will happen? And before that, from expression here, we see that this expression W is a universal proportion of A. If slit width is very narrow, so this central fringe is very high, very broad actually. So intensity is very high. Okay, and here, so W is very high means the lambda is also very high. And if the screen is very far distance, D is also very high. So obviously W is very high. Okay, so here we get some common concept from equation. Here we get a W is inversely proportional of 1 by A, and W also directly proportional to lambda. If a wavelength also high, so central fringe width also be the high. Okay, so now if I combine these two, what will happen? So see that if I combine these two, very important concept. If suppose a gap here, obviously single source of light passing from two slit here. Okay, so now these are S, and that is very small gap with that A. Now put a screen here. These are the screen. We get from diffraction pattern. First they get a diffraction pattern, and from due to diffraction we get some central fringes here. Suppose we get spot here. The central fringes look like this. And that's a very high intensity. Okay, so now very high intensity, and here that some intensity much lower, the gain is lower, and so on. Here we get some so on. Okay, so here it get a diffraction pattern. This green color line is intensity of diffraction. A single slit envelope. These are a single slit envelope. Okay, so the width here, this width, actually this width this width W, that is equal to twice lambda D by A. Okay, that's actually we get from diffraction. Okay, now here these two single slit S1 and S2, suppose say that is a S1 and S2 also produce an interference here. So now the interference is inside that envelope and it look like this. And the high intensity. uh, So now we get, okay. So this red color represent for interference, and now the width here we get some spot here, okay, and now the spot here we get some spot. That these spot length are be the same here. Okay. This length be the same, and here we get no spot, very spot, but here we get same length of fringes here. Now no fringes here, and here very small length here. Okay, and here we get very small. Yes, no fringes here. Here fringes is length is very small, and now this width of these fringes, this width of the fringes, the W, that is equal to lambda small lambda capital D by S, and S is the gap between two slits. Okay, so that's the combining interference and diffraction pattern. We get some interference pattern is inside the diffraction pattern. Obviously, the single slit here they also produce a diffraction. Okay, if these two sources are incoherent, obviously they are incoherent because the sources be the same here. We use of help of Young experiment here. Okay, so these for interference and these for diffraction. Okay, so now in next page we put some real image here. Okay, so here you see that that's the diffraction. Okay, and here you see that from the intensity actually they are very high, and that is the central fringes, and from left side you see that that is intensity is very much lower here. There is a maximum intensity. Now intensity is very low, almost negligible here, very high. Okay, so that's the diffraction pattern is originally look like this for image. Okay, there's a diffraction pattern. These are for diffraction, and if I combine these two for diffraction inside the interference, that's the actually that interference, that's actually a diffraction here, the central fringes. Now the width is very much lower, and here we get some another fringes here. Actually these are not combined, these are the interference, that's the diffraction. And you see that fringes are in same width, but in diffraction from central fringes to what if I increase that, so length here, so like that, from interference here for diffraction upper side, you get some width is central actually fringe width is very much lower here. Okay, so clear what is a diffraction and what is interference, what is the difference between diffraction and interference here. That is for diffraction, that is interference, and that is diffraction. Okay, so I think now that clear the concept, what is a diffraction, what is interference. If you have any doubt, please ask in comment section. I'll try to give the answer. Okay, so next class we discuss another important concept is the polarization. That's very important in wave optics. Okay, so today in the class here, thank you.